Yes, unfortunately, I
Okay, I'm going to go ahead and get started. Today's class, we're moving on. We're moving on from electricity, we're moving on from magnetism, and we're moving on from light. We're moving on from the complete theory of electricity and magnetism, electromagnetism that includes electricity, magnetism, and light, to shine light onto space and time, that's this week, and shine light onto matter, atoms and molecules. That'll be next week and the following week. So we're going to use our understanding of electricity, magnetism, and light to explore the world of space and time this week, explore the world of matter, atoms, molecules, subatomic particles, next week and beyond. That's the plan. Today's class, I want to cover these bullets on the overhead. I want to introduce relativity, and I want to introduce space and time in relativity. We'll start by looking at the sort of foundations of relativity. I'm going to talk about this is one foundation of relativity. It's called the invariance of the laws of physics, and I'm going to explain how we use the word invariance. The second foundation of relativity is the invariance of the speed of light. Again, better explain exactly what I mean by invariance. We're going to talk about two features of relativity, perhaps the two most famous features of relativity. One is time dilation. We're going to explore what time dilation is, what it means, the significance of it. Second one is length contraction. We're going to explain what length contraction is, see what it means, explore the significance of it. And then we're going to look at an example of relativity, an illustration of relativity. It's a famous example, illustration of relativity. It's an example about space travel from Earth to some distant, far off location in outer space. We're going to go to a star that is 4 light years away, and we're going to explore that trip, that travel. So that's the plan for today. As you probably know, unless you were living under a rock, Albert Einstein was the inventor, discoverer of relativity, of the new picture of space and time in relativity. One of the really interesting things about relativity and this new picture of space and time, in one sense, it's the kind of easiest, most straightforward of physics topics. In another sense, it's the most complicated, hardest of physics topics. The theory is just based on a little bit of high school algebra. So there's nothing whatsoever mathematically complicated about relativity and space-time. However, conceptually, the theory, it goes against our common sense. It goes completely against our intuition. So it's not a mathematically complicated theory, but it's conceptually a very difficult theory. And so we'll see that today. There's not much math in today's class. There's no complicated math in today's class. But there are new ideas, concepts in today's class that are really hard to wrap your head around. They're hard for me to wrap my head around. I'm sure they'll be hard for you to wrap your head around. We all struggle with the concepts, the ideas of relativity. Okay, so first part of the class is just to introduce the bases for relativity, the foundations of relativity, the cornerstones of relativity. What are the ingredients that go into relativity? And as I mentioned, there are two of them. One has to do with the laws of physics being so-called invariant. The other one has to do with the speed of light being so-called invariant. So we'll discuss those. Let me mention, and I think you'll agree with this once you see these two foundations. One of these, the fact that the laws of physics are invariant, is if that wasn't true, then that would be ridiculous. If the laws of physics weren't invariant, that would actually be ridiculous, and our whole notion of physics and the science would just collapse. So this first one, if it was false, it would just seem very strange to us, very weird to us. We wouldn't believe it. The second one is the reverse. The invariance of the speed of light, constancy of the speed of light, if that were true, if that one were true, that would seem really weird to us. How could the speed of light be constant, seen as the same value to all observers? This is one that is the reverse. It would be really, really strange if this was true. But these two ideas are the bases for relativity, out of which relativity is constructed, that the laws of physics are invariant and the speed of light is invariant. So we're going to see that. To discuss these things, I've got one slide just to introduce something you probably met before, but I want to talk about it again. I want to introduce it again because it comes up as a very important basis for relativity. It's the idea of reference frames. So in physics, a reference frame is just a coordinate system. A reference frame would have, in general, spatial coordinates, and it would have a time coordinate. And using those space coordinates and those time coordinates, you could specify the location in space and in time of some sort of event, right? So we use reference frames in physics. We use coordinates, space and time coordinates in physics to specify locations of events. In this slide, I'm picturing two reference frames, and I'm sketching two reference frames so that we can get an idea of this importance of two reference frames. If you want an example of two reference frames, I've pictured an example here. This picture here is of a train that's passing through a station. It's traveling through the station. The train's not stopping at the station, it's passing through the station. And it's an example of two different reference frames, two different coordinate systems. One of the reference frames, coordinate systems, is the platform reference frame. So if you're standing on the platform, you're stationary in the platform reference frame. That's a perspective from which you could describe the position in space and time of objects, and that would be the platform reference frame, a platform coordinate system. Another reference frame in the picture is the train reference frame. Supposing you're on the train, right? That is also equally good reference frame. Using the train reference frame, the train coordinates, you could specify the position and the time of an event. So the picture of the train passing through the station is a picture of two reference frames, the platform reference frame, the train reference frame. They're both valid reference frames. They both have coordinate systems. They can both be used to describe the locations of events. We tend to think when we look at the picture as the platform reference frame as the one that is stationary and the train reference frame as the one that is moving, but that's just from the perspective of the platform. We could equally well think of the situation from the train perspective. Then if you're in the train reference frame, you're stationary in the train reference frame and the platform is moving with respect to you. So the train and the platform reference frames are equally valid, and you can consider one as moving and the other as stationary. We could consider the platform as stationary and the train as moving, or vice versa. We could consider the train reference frame stationary and the platform reference frame as moving. Both of those are equally valid. They are what we call, and what we're going to be talking about today, they are called inertial reference frames. So inertial reference frames, inertial is just code word. It just means a reference frame that's moving at constant velocity. It just means a reference frame that's not accelerating. So the reference frames I'm talking about is when the platform reference frame and the train reference frame, they're moving at constant velocity or stationary. They're not accelerating, and that's what we call an inertial reference frame. Okay. So now I've got two slides in which we're going to look at a ball being thrown into the air. And we're going to look at the ball being thrown into the air from two different reference frames, two different inertial reference frames. The first one that we're going to look at the ball being thrown into the air is from what I'm calling the passenger reference frame, where the passenger is the person in the back of this truck. And then the second reference frame, I'm going to look at the ball being thrown into the air, is from the what I'm going to call the pedestrian reference frame. It's going to be from the frame of reference of a pedestrian standing on the roadside watching the truck go by. So we're going to see the same thing, the ball being thrown into the air and falling back down, but from these two different reference frames. And remember, these reference frames allow us to specify the events, the position in space and time of events. They allow us to describe the trajectories in space and time of the ball as it moves through the air. And we're going to look at the ball moving through the air and understand the motion of the ball through the air and ask the question, what things are relative to your reference frame? And what that means is that they would change from reference frame to reference frame. What things are invariant or absolute in the reference frame? That means invariant or absolute would mean that they didn't change when you went from one reference frame to the other reference frame. So we've got two reference frames, passenger reference frame, pedestrian reference frame. We're going to be asking who's relative, who changes from frame to frame, and who's invariant, who's absolute, who stays the same from frame to frame. Okay, so passenger reference frame. Here's the truck moving down the road. Here's the person in the back of the truck. I wouldn't recommend doing this, but throws the ball into the air, and the ball comes back and catches the ball. In this reference frame, imagine we're in the passenger reference frame. We see the ball go straight up, vertically upwards, and come straight vertically back downwards. That's the path that we see. That path, the position of the ball versus time as it goes straight up and then comes straight back down. Also, the speed of the ball as it goes straight up and comes straight back down, both the speed and the direction. So the velocity of the ball as it goes straight up and comes back down, those are relative quantities. we're going to see that those quantities, the position of the ball, the velocity of the ball as a function of time, that describe the trajectory of the ball as a function of time, they will change from frame to frame, from reference frame to reference frame, between, for example, passenger and pedestrian reference frames. So the position of the ball, the velocity of the ball are examples of relative quantities. There's other things, though, that are absolute, invariant quantities in this picture. The physics behind the ball going up into the air and coming back down, the physics behind that is the law of gravity. That's one piece of physics that describes that motion. The other one is Newton's laws of motion, describes that motion. Those laws of physics, Newton's law of gravity, Newton's laws of motion, those are invariant, absolute things. They're not going to change. They won't change as we go from one frame to another frame. They're true in this frame, the passenger frame. They'll be true in the pedestrian frame. So as we look at this picture, we can see things that are relative, the position, velocity of the ball as a function of time. We can see things or understand things that are absolute. For example, the law of motion, the law of gravity are not going to change from frame to frame. Let's jump to the next frame. Here's the same ball and the same motion in Earth's gravity, but now viewed from a different reference frame. It's viewed from the reference frame of the pedestrian here, watching the truck go by. So now the pedestrian sees the ball's motion not as straight up, straight down motion, but rather a curved, an arced motion that is both up and down and left and right. So this is telling us that the position as a function of time of the ball, the velocity as a function of time of the ball, is a relative thing. The pedestrian sees different, in their reference frame, with their coordinates, sees different position as a function of time, different velocity as a function of time. That's why I labeled this x and this v with the primes here. However, behind the scenes, explaining that motion of the ball, that curved arc motion of the ball, the laws of physics, the law of gravity, the laws of motion, they're absolute, they're invariant. The pedestrian sees the same law of physics as the passenger did, has the same explanation for the motion as the passenger did. So the laws of physics are the same. So that's the first key ingredient in relativity, is that all observers, no matter your reference frame, no matter your inertial reference frame, whether you're the pedestrian or you're the passenger, you see the same laws of physics. So that's a very key, that's a cornerstone of relativity. The second one, cornerstone of relativity, has to do with the speed of light. And this one's that the speed of light is also an absolute invariant quantity. And this is the strange one. This is the very strange one. This is a very unnerving one, because it doesn't seem like it makes common sense. There's no intuition that the speed of light would be the same in different reference frames. To give you an example of that, here's something that an example of something that's similar. It's another wave. It's sound waves rather than light or light waves. So it's also a wave moving through space and time. And a sound wave, we talked about it in the last class. If you have a speaker and you produce some sound, if you measure the sound speed in the reference frame of the air, in which the sound is vibrations, oscillations in the air, you would measure a speed of 340 meters per second. That's the speed of sound. But if you were to move through the air, and measure the speed of sound, you would see, in general, a different speed of sound. For example, if you run towards the speaker at 40 meters per second, you would see a greater speed. If you run away from the speaker at 40 meters per second, you would see a reduced speed. So here's an example of the sound waves. Their speed is a relative quantity. Their speed depends on your reference frame. It depends on whether your reference frame is the reference frame of the air, in which you're going to see 340 meters per second because the sound waves are oscillations in the air, or your reference frame is not the air. You're moving to the right through the air, or you're moving to the left through the air. Then you'll see different speeds. So sound speed is a relative quantity, and that makes a lot of common sense as we imagine the sound moving through the air. But light, on the other hand, has this peculiar quantity, peculiar feature that all observers measure the same, whether they're the pedestrian or the passenger, or they're in the two rocket ships here traveling to the left and right. They all measure a light ray traveling with the same speed, exactly the same speed. So in this slide here, the spaceship on the left is traveling towards the left, towards the flashlight, towards the source of light, kind of like one car was traveling towards the left, towards the loudspeaker. The spaceship on the right is traveling towards the right, away from the source of light. The occupants, the astronauts in the spaceships, measure the speed of light, the speed of these light rays that are emerging from this flashlight. And strangely, they find that they both agree exactly. No matter how fast this spaceship travels towards this light, or this one travels away from this flashlight, they always measure this same speed of light. If this spaceship, this is the craziest thing, if supposing this spaceship on the left was to travel towards the flashlight at 99% of the speed of light, supposing you could build a spaceship that can travel towards the left 99% of the speed of light, what would it measure this light rays to be traveling at? Even though it's heading towards the flashlight, 99% of the speed of light, it measures them traveling at the speed of light, 3 times 10 to the 8 meters per second. If this spaceship also was able to travel at 99% of the speed of light, it's traveling 99% of the speed of light away from the flashlight, what would it measure the light traveling at from the flashlight? It would also measure the light traveling at the speed of light, 3 times 10 to the 8 meters per second. So this is very peculiar. So light, the speed of light in relativity, is one more thing in addition to the laws of physics that is now invariant. And that's not common sense. It's against common sense. That's not intuitive. It's non-intuitive. But that's Albert Einstein's basic idea on which he developed a new understanding of space and time. So that's a key ingredient for us. Just to give you one more illustration of relative quantities and absolute quantities, relative quantities and invariant quantities, because that's really important in relativity to distinguish between them. Here's just a little cartoon. So we got Bill and Ben. Bill's on the left here. Ben's on the right here. And they're looking at this number on the ground. And Bill says this number's a 6. Ben, looking at the same thing, says this number's a 9. That number on the ground is a relative thing for them. It depends on their measurement of the number. Their understanding of the number depends on their frame of reference. And so, you know, Bill is interpreting as a 6 and Ben's interpreted as a 9, or vice versa. So the number is a relative thing. But there's something that's absolute that's inferred in this picture. 6 plus 9 is 15, that's invariant. They would both agree that 6 plus 9 is invariant. So this is kind of analogy to position and velocity for the pedestrian and the passenger. That was a relative thing, like the 6 and 9 interpretation of the number for Bill and Ben. That's a relative thing. But the pedestrian and the passenger agree that the law of gravity and the laws of motion describe the situation. And in this picture, Bill and Ben agree that basic mathematics, basic arithmetic means the sum of 6 and 9 is 15. Another example, I think I do kind of my fair share of the washing up, but my spouse seems to think that I haven't done the washing up for 20 years. So we have different interpretations of what fraction of the washing up we do. So that's a relative thing, right? In any relationship. Your fraction of the washing up is your interpretation of your fraction of the washing up. I remember the time that I did the washing up, so I count that, but I can't remember when my spouse did the washing up, so I might dismiss that a bit. So that's a relative thing, but you probably agreed that overall the washing up did get done. So the washing up did get done. That's an invariant quantity. Who did it? That's sort of an interpretive quantity, a relative quantity. Okay. So we talked about the basis of relativity. Now I want to start to introduce the strange nature of space and time that is based on these foundations. As I say, the foundation that speed of light is constant and that the laws of physics are constant. So this slide is meant to introduce the fact, to motivate the fact that we're going to have to change our notions of space and time in order to fit in with the laws of physics being absolute and the speed of light being absolute. The only way we can fit in with the laws of physics and the speed of light being absolute is to really fundamentally change our notions of speed and time. And this illustrates this. So in this picture, I've redrawn the source of light, the flashlight, the space rocket that's traveling towards the flashlight, the space rocket that's traveling away from the flashlight, the fact that they both measure the same speed, the speed of light, 3 times 10 to the 8 meters per second. I've redrawn that, but I've added onto the figure some details, the reference frames for the 2 spaceships, and the details of their measurements of the speed of light for the 2 spaceships. And so I just want to walk through their measurements of the speed of light so that we can see what would have to change for them to agree that the speed of light is same. So right now we're thinking that it can't be that the speed of light could be the same for the 2 astronauts and the 2 spaceships. That just doesn't seem common sense. It doesn't seem intuition. But there is a way that the speed of light could be the same, invariant, absolute, for the 2 astronauts in the 2 spaceships. And there is a way by fixing up our notions of space and time. And so we're going to see how we might have to fix up our notions of space and time. How do the astronauts measure the speed of the light ray? I mean, how do you measure the speed of a light ray? Well, the way these 2 astronauts are measuring the speed of light ray, which is maybe how we might measure the speed of a car going by or a pedestrian going by, is to use the definition of speed. That is the distance traveled divided by the time taken. So that's the basic thing you're going to use, the meaning of speed. That's a law of physics. When you measure the distance traveled and divided by the time taken, you need 2 reference points. And so they're going to use these 2 flags here. The light passing flag number 1 on the left, that's kind of an event, a moment in space and time. And in their reference frames, the two astronauts are going to record the times and the positions of that event, the light ray passing the first flag. And then when the light ray then passes the second flag, that's a second event in space and time. It's occurring in space and time. The two astronauts will also record the times of that event and the locations of that event in their reference frames. So they're going to measure the speed of the light ray by measuring the times and positions of the light ray passing the first flag, and then the times and positions of the light ray passing the second flag. Then what they're going to do with that information? Well, with that information, each one of them, armed with the positions of the times of the two events, they can figure out from the difference of the positions the distance traveled for the light ray. So I called that delta x and delta x prime for the two reference frames. For the spaceship traveling to the left and the spaceship traveling to the right, they're going to figure out the distance traveled for the light ray between the two flags as measured in their reference frames, delta x prime. They're also going to figure out the elapsed time between the two events as measured in their two reference frames. So the left-going and the right-going astronaut are going to figure out the time difference between the two events as measured by the clocks in their reference frame. So they'll do that too. So at that point, they figured out the distances traveled as measured in their reference frames. They figured out the time taken as measured in their reference frames. All they got to do then is divide the distance traveled divided by the time taken, very basic law of physics, as speed equals distance traveled divided by time taken, to calculate the speed. And when they do that, when they calculate dx divided by dt, this is the distance traveled divided by time taken for the astronaut that's going towards the left. And when they calculate dx prime divided by delta x prime divided by delta t prime, that's the distance traveled divided by the time taken as measured by the astronaut going towards the right. The amazing thing is that they find they both get the same speed. I called it c and c prime in the two reference frames, but it's the same, exactly the same speed. The only way, so this is telling us that to get the same speed for astronaut going towards the left, astronaut going towards the right, to get the same speed, there must be something that is strange, counterintuitive, non-intuitive about their measurements of the time interval between passing the two flags and the spatial distance between the light passing, the two events corresponding, the light passing the two flags. And so we've got to fix up space and time if we're going to explain the speed being absolute for light. And so that's what we're going to do. Okay, so what we've concluded here is really that there's something strange about space and time, something strange about, non-intuitive about space and time in relativity. And there's actually two effects I'm now going to describe. One is called time dilation, the other one is called length contraction, that really, these two effects really capture the strangeness of space and strangeness of time. And these two effects, time dilation, we'll see what that means, we'll see why that captures the strangeness about time measurements, and then length contraction, we'll see why that captures the strangeness about distance measurements. And so we're going to discuss these two effects, and this is going to be kind of the core of our understanding about the strangeness of space and time in relativity. Okay, we're going to start with time dilation. I've got a few slides on that, and then we're going to talk about length contraction. I've got a similar few slides on that. So this is a situation that we're going to consider in this picture here. It's going back to that early slide where I introduced inertial reference frames, and the example I gave was a a train passing through a station where there was a platform reference frame, and then there was the train reference frame. So in this slide, I'm picturing a platform reference frame, a station reference frame, and a train reference frame. So here's meant to be the platform, and this green observer here is the station observer, the platform observer, that's at rest in the platform. And then upstairs here, this is meant to be the train. And this orange observer is the occupant of a train at rest in the train, sitting in the train. So this is an example of two reference frames, as we've discussed. In green here, this is the platform reference frame. Here's the vertical axis is the time. That's where time ticks past vertically. Horizontally is the position. This is the x-coordinate horizontally. I'm only drawing one space dimension. Obviously, there's two more space dimensions, but we only need one to understand the effect. And then upstairs here, the orange reference frame is the same sort of thing, but for the train observer, the passenger reference frame. So vertically is the time axis, horizontally is the position axis, and with this reference frame, we can locate events in space and time in the passenger reference frame. To distinguish between the two, I mean, the one's green and one's orange, that's distinguishing between the two, but I've labeled the one downstairs, the platform reference frame, the coordinates are x and t, the train reference frame, the passenger reference frame, the coordinates are x prime, t prime. So that distinguishes the two reference frames. In the platform and in the train is what we're going to call the station clock and the train clock. So every station has a clock on the wall. That's the station clock. A lot of trains have a clock in the carriage. That's the train clock. So there's a clock, the station clock, that's at rest in the station reference frame. There's a clock in the train that's at rest in the train. It's the rest in the train reference frame. So there's these two clocks here. This one I pictured here, and this is the station clock. This is upstairs here. This is the pedestrian clock. Now, in this slide, and this is going to change in the next slide, I've drawn the slide from the perspective, from the viewpoint of the observer on the platform, the station reference frame observer. You can see that I've done that because look here. This velocity vector is indicating the motion of the train. So in this slide here, the train is moving left to right. The platform is stationary. And that's something we're going to change in the next slide. So this is drawn from one perspective. The key thing in relativity about time measurements is this feature I called time dilation. Time dilation is an effect that occurs when you measure a time interval between two events. Now, the time interval between two events might be the time between two ticks of a clock. That's the example we're going to think of. Time dilation is an effect that occurs when those two events are at different locations. For example, if the clock was moving. So let me describe time dilation here. If this observer, the platform observer, the station observer, looks at the station clock, the platform observer looking at the station clock measures that the station clock ticks with the correct time. The interval between seconds is the correct time for the station observer, the platform observer looking at the station or platform clock. The observer in the train, however, who's going to see this clock moving, because that observer is moving, that observer in the train sees the clock tick slower. That's time dilation. So the clock ticks slower for the observer in the train, slower in reference to his reference frame, which means his clocks and meter sticks and so forth. So this observer is seeing this moving clock ticks slowly. This observer is seeing the stationary clock in the station tick correctly at the proper rate. The equation describing the slowing down of the ticks observed by the observer in the train of the station clock, of the moving clock, the equation that describes it is this little equation here. So this is the equation of time dilation. It says that, to apply to this situation, it might say that the time interval between ticks of the clock on the station, as measured by this observer who's seeing that clock as moving, those ticks are the time interval between them is the time interval, the proper time between them, as seen by this observer in green that sees the clock as stationary, divided by this quantity, the square root of 1 minus v squared over c squared. Now, this is a division by a quantity that's going to be smaller than 1, right? This number here is bigger than 0. So 1 minus this number is going to be smaller than 1. So the denominator is smaller than 1. That's going to make the time interval t prime longer than the time interval t. So this dilates, stretches out time, this effect. Inside the square root here, there's two speeds, if you look at it. One speed is the speed of light. It's kind of a reference speed. The second speed is the speed of this observer's motion, or the speed of this clock as it moves with respect to this motion. And so this is comparing those two speeds. If you think about it, this means that for everyday speeds, this is a tiny or negligible effect, right? A train's motion through a station is much smaller than the speed of light. So v is much smaller than c. So v squared is much smaller than c squared. And so this is a very small effect. But if you had speeds that were, if the train could go at speeds near the speed of light, where v was near c, then this would be a much larger effect, and time would stretch out. The time between the ticks of this clock on the station observed by this observer that's moving by would be stretched out in time. And so this is time dilation. A key thing about it is that we kind of inherently assume, it's common sense, right? It's intuitive that if you look at a moving clock, it still ticks at the same rate. The time between successive ticks is the same time interval. But actually in relativity, the time between successive ticks, the rate at which the clock ticks, a moving clock ticks, is not exactly the same. Now, it's nearly exactly the same if the clock is moving at everyday speeds, but if the clock is moving at very high speeds on the scale of the speed of light, then that clock ticks much slower. And that's a feature of relativity. We don't see it in our everyday lives. We don't experience it in our everyday lives, so it doesn't seem that that could be common sense. Right? That's not intuition, but it's a reality about the nature of space and time. That a moving clock, a high-speed moving clock, will be seen, observed, to tick at a slower rate. This is the same slide. This is exactly the same slide, but I've changed the perspective on this slide. The last slide had the train moving through the platform, and we took the perspective, we were viewing it from the platform perspective. In this slide, train is moving through the platform, but we're taking it from the perspective of the train perspective, the train reference frame. So in this slide, the train is at rest, but the platform is moving. The platform is moving from the right towards the left across the room here. And so that's an equally valid perspective to use the perspective of the train reference frame. And the other thing I've changed in this slide is, in the last slide we were looking at the station clock. The person on the platform saw the station clock as stationary, and it measured the proper time between seconds. The person in the train saw the station clock as moving, and that's where we saw the time dilation effect. In this case, we're going to be looking at the train clock. The person on the train sees the train clock as stationary, and the person on the train looking at the train clock will see the train clock tick with the proper interval between successive ticks. The person on the platform, however, is seeing the train clock moving and will see time dilation for the moving train clock. So all the roles have reversed here. Before, in the last slide, it was the passenger in the train that observed the time dilation of the moving clock. In this case, it's the pedestrian on the platform that is going to experience time dilation for the moving clock in the train. So observer in orange here in the train says this clock ticks at the correct rate, correct interval between ticks, but the observer on the platform looking at this clock says that, and with respect to their own clock, that this clock is ticking slowly. They're observing time dilation, the stretching of time between successive ticks of the clock, and it's described again by the same formula here. This formula is that now the observer in green observes, for example, the time between two ticks of the train clock will be the time between two ticks of the train clock as measured by the observer in the train, seeing the clock as stationary, divided by this factor again, this factor here. This factor, just to stress again, that's in the denominator is going to be smaller than 1, because v squared over c squared is always bigger than 0 or bigger than 0. So inside the square root is always smaller than 0. So it's going to increase the time interval between successive ticks, as seen by this observer watching this moving clock. And so this is again time dilation, but now it's not only does the person in the train see the time dilation for the station clock because it's moving by. The person on the station, on the platform, sees time dilation for the clock in the train because it's moving by. So it's sort of symmetric in that way. Both observers measure their own clock as ticking at the correct rate. Their own clock is the one that's stationary with respect to them. Both observers see the other clock, if I'm on the platform, the one in the train, if I'm in the train, the one on the platform, moving, ticking slowly, seeing time dilation. This factor is a very famous factor in relativity. This factor comes up all the time in relativity. We don't want to keep writing down this factor of square root of 1 minus v squared over c squared. In a sense, in this case, it's really the multiplication by 1 over the square root 1 minus v squared over c squared. So we compactify it. We give it a symbol. This symbol gamma here is called the Lorentz factor. 1 over square root of 1 minus v squared over c squared is the Lorentz factor. The Lorentz factor 1 over the square root of 1 minus v squared over c squared is something that is 1 or bigger. It's 1 if v equals 0. It's a little bit bigger if v is not 0, if it's everyday velocities, just a tiny, tiny, tiny bit bigger. It can get really big if v is of the order, the scale of the speed of light. Then you can get much, much bigger than 1. So it's a number that's 1 or bigger that reflects the speed of the motion measured basically in units of the speed of light. So that's the Lorentz factor, and that's time dilation. So that's the whole effect of time dilation described in that one simple formula. It's not a so this is a point I tried to make at the beginning. This is not a complicated math equation. It's a straightforward equation for calculating the dilated time from the proper time, but it's conceptually it's really difficult to understand how this could be. How can both observers see the other clock, the moving clock, run slowly? That seems paradoxical. I'm on the station, I see your passenger clock run slowly. I'm in the train, I see your platform clock run slowly. Both sees the other's clock run slowly. That doesn't make any sense, but that is actually reality. This is just a picture of that factor, gamma, of the Lorentz factor, that turns proper times into dilated times when the clock starts moving. So it's just a picture of that factor as a function. What's it a function of? It's a function of velocity. So it depends on velocity. And so horizontally here, I'm plotting velocity. I'm plotting it in unison to the speed of light. So this is from 0, velocity 0, to 1, which means velocity would be the speed of light. And vertically, I'm plotting the Lorentz factor, this multiplying thing that turns proper times into dilated times. At low speeds, so we live right down here, you know, right in this corner here, everyday speeds. At low speeds, Lorentz factor is 1. This is why it seems strange to us, counterintuitive to us, not common sense to us, because we don't live in this world, basically. We live in the world of everyday speeds where v is nothing compared to the speed of light. But if we live somewhere up here, if we had speeds of the scale of the speed of light, electrons live in that world, for example. In atoms, they live in a world upstairs here. To them, this is all old hat, right? With special relativity, because they live in that world. It's their everyday experience. So as you increase v, the effects of time dilation grow and grow and grow. And look, if you were going at 90% of the speed of light, that clock is going to run 2.5 times slower. So this can become a big effect. If you were going at 99% of the speed of light, somewhere up here, that clock would be running about 10 times slower. So it becomes a huge effect, time dilation at high speeds. I want to show you a little overhead that shows this time dilation of a moving clock. And it's based on a type of clock that we call a light clock. Yeah. So a light clock is an arrangement where you've got two mirrors. So there's a mirror over here on the right, mirror over here on the left, and a pulse of light is sent between the mirrors. And we're going to watch this pulse of light bounce back and forwards between the mirrors, and one tick of a light clock is the time it takes to go from the left to the right and then back to the left. That's one tick. So you'll see this light clock ticking, and you can imagine what a tick of the light clock is. And then what are we going to do? We're going to move the light clock. I'm going to move it vertically upwards. And as it moves upwards, you're going to see the ticks slow down. The ticks slow down because whether the light clock is not moving or whether it is moving vertically, the speed of light is always constant. And so you'll see that when the light clock travels up and the light speed remains constant, it's going to take longer between ticks. And you see a light clock does tick more slowly. So this is a sort of physical understanding of why clocks would tick more slowly. Here's an example of a clock ticking slowly. It's a light clock. So watch this light ray go backwards and forwards. That's one tick. Then here comes the next tick. That's the second tick. There's a third tick. There. fourth tick. Now we're going to move upwards. This light ray has to also go upwards. It's got to travel further, but it's still traveling at the same speed. So if you were to count the time between those successive ticks of the moving clock, it would be a smaller time, a longer time. Let's watch it one more time. Think about the time between ticks. And see if you can picture how that time slows down when we move the clock up. It's taking a longer time to get from mirror to mirror, which means that the clock ticks have slowed down, which means there's time dilation. Okay, so that's one ingredient that we didn't expect, time dilation. The second one that we wouldn't have expected is what's called length contraction. And you'll see it's a kind of similar effect, but in the world of space rather than in the world of time. So let's look at length contraction. This thing stopped working. I've got two slides to show you length contraction. I'm going to go through this a bit more quickly because it's very similar to time dilation. Length contraction, time dilation are like cousins or brothers and sisters of relativity effects on space and time. We're back on the station with the train passing through again. This is a picture of the situation from the perspective of the platform reference frame. The platform is stationary and the train is moving. This is the velocity vector of the train from left to right. Now I've replaced the station clocks and the train clock for measuring time intervals. I've replaced them with, there's a station meter stick. And there's a train meter stick for measuring distances on the train and the station. So trains and platforms also carry meter sticks for measuring distances. There's a platform meter stick that's here, and there's a train meter stick here. We're going to focus in this slide on the platform meter stick, and in the next slide on the train meter stick. So if we focus on the platform meter stick, the platform observer sees that meter stick as stationary. They're going to measure the proper length of the platform meter stick. They'll measure the proper length. We'll discover through this equation that the train observer, in orange here, train observer is going to see the platform meter stick moving. It's going to be moving towards the left. They see the moving meter stick as not having the proper length, but rather having a shorter length. It's length contracted. This is the sort of spatial equivalent of time dilation. So to summarize, the observer who sees the stationary meter stick, the station observer looking at the station meter stick, sees it have the proper length, 1 meter. The observer in the train, however, with their reference frame, measures the length of the meter stick to be not the proper length, measures it to actually be contracted, shorter. L prime here is the contracted length that's measured by the train observer for the moving meter stick. It's a fraction of the true length. It's contracted from the true length. This L in green is the true length of the meter stick, or it could be the true distance between two events. And the contracted length is equal to the proper length times this factor again, where we see again this square root of 1 minus v squared over c squared. Although in this case, to get the contraction is in the numerator, to get the time dilation, remember, is in the denominator. So square root of 1 minus v squared over c squared, again, the v squared over c squared is going to be 0 or bigger as we watch the moving meter stick. So it's going to be, it's going to be bigger than 0. Yeah, v squared over c squared is going to be 0 or bigger, which means that 1 minus v squared over c squared is going to be 1 or smaller. So this quantity here is smaller than 1, and so it shrinks the length of the meter stick as measured by the observer in the train who's seeing the moving meter stick. And so this is why we call that effect length contraction. Again, it's handy to write it in terms of the Lorentz factor, this symbol gamma. This time, instead of time dilation, you would multiply by gamma to get the time dilated time from the proper time. Length contraction, you divide by gamma to get the contracted length from the true length. So remember, gamma is bigger than 1. To get the contraction, you're dividing by gamma. To get the time dilation, you're multiplying by gamma. So that's the perspective of from the platform perspective. This doesn't work. This is the reverse perspective. Now we're focusing on the meter stick in the train. Here's the meter stick in the train. And we're going to look at the meter stick in the train from the train reference frame, this observer, and from the station reference frame, this observer here. To stress that, look, in this picture, the train is stationary, the platform is now moving from right to left. So the platform's streaming over towards the left-hand side of the classroom. The proper length of the meter stick is measured by the meter stick in the train is measured by the train observer. So this observer sees a stationary meter stick, measures the proper length. The contracted length of the meter stick in the train is seen by the station observer, who sees that meter stick as moving. So they see the contracted length. This is the equation for the contracted length as seen by the platform observer of this moving meter stick. So it's the proper length as measured in this reference frame, the train reference frame for the train meter stick. That's this sort of brown-colored L prime here, multiplied again by the square root of 1 minus v squared over c squared, or equivalently divided by the Lorentz factor gamma. And remember, this factor gamma is bigger than 1. So multiplication by 1 over gamma is going to shrink the proper length to the contracted length. So the platform observer is seeing a contracted length of the moving train meter stick. So this is again funny, right? Remember that the train observer saw time dilation for the moving clock on the station, but the station observer saw the time dilation for the moving clock on the train. So they both saw the others' train clocks tick more slowly. The same is true here. The train observer sees the station clock, a station meter stick, as contracted. The station observer sees the train meter stick as contracted. They're both seeing the other's meter stick get contracted. They see their own meter sticks as having the proper length. And so that's length contraction. So these two effects, length contraction and time dilation, are the two ways in which our notions of space and time are changed in relativity. So they're kind of the foundational effects in relativity that affect our measurements of space and time. And they're at the heart of explaining why, measuring the speed of light from two different reference frames, the spaceship traveling to the left and the spaceship traveling to the right, could yield the same speed of light. If you incorporate time dilation in your time interval measurements, if you incorporate length contraction in your distance interval measurements, then you end up with both observers, the left-going, right-going rocket ships, measuring the same speed of the light ray, no matter how they're moving with respect to the light ray. Let's look at an example. This is just a plot of that factor that shrinks the length of the meter stick when you observe the meter stick. This is just a plot of 1 over gamma. That's the factor by which the meter stick is contracted. The last plot I showed you was just a plot of gamma, which is the stretching of the time interval that describes time dilation. So this plot and the previous plot are just gamma plotted versus speed and 1 over gamma versus speed. So really the same quantity I'm plotting in two different ways. In the case of gamma, gamma grew from 1 as you went towards the speed of light. In the case of 1 over gamma, of course, if gamma grows, then 1 over gamma will shrink. So gamma shrinks from 1 at everyday speeds towards 0, squeezing, contracting the thing to nothing at very high speeds. Right, I want to solve this problem. Good luck. Okay, here's a famous example. We've got an astronaut, they're traveling from Earth to a distant star. It's 4.2 light years away. I'll explain what this distance is in a moment. They're traveling from Earth to the star, and here's their spaceship, and we're told that their spaceship travels at 95% of the speed of light, 0.95 c, with respect to Earth and the star that they're going to. There's two reference frames in this picture. So in this picture, there's kind of the home reference frame. So I'm the spouse. I had to stay at home. I wanted to go to Alpha Centauri, but no, I've got to stay at home, look after the cat. So I'm the one that's at home. That reference frame is the Earth sort of Alpha Centauri reference frame. It's the home reference frame. It's kind of like the station reference frame. Then there's another reference frame. There's the astronaut exciting reference frame. That's the one that is speeding in this picture, from left to right at 95% of the speed of light. We're told the distance. I'll explain how we're told the distance here. Between Earth, where we leave, and Alpha Centauri, where we arrive. And we've got to figure out the time recorded by the astronaut for the trip, the time recorded by the, good luck, time for the spouse as to how long the trip took. And if we get time, we're also going to figure out the distance as measured by the astronaut between where they started and where they ended up. I just want to mention that I'm describing the distance between Earth and Alpha Centauri in a unit of distance called light years. We sometimes write light year. This is a compactified light year. C is light, right? Light year. It's 4.2 light years. What is a light year? Where did that come out of? A light year is the distance traveled by light in 1 year. So 3 times 10 to the 8 meters per second is 3.10 10 to the 8 meters is a light second. That's the distance traveled by light in 1 second. But you could also figure out the distance, this enormous number, light traveled in 1 year. That's a light year. That's a distance. A light year is a distance. And so it's a way of measuring distances when distances are very big. 1 light year is 3 times 10 to the 8 meters per second times the number of seconds in a year, which I've figured out for you here. It's about 10 to the 16 meters. So it's a way of measuring really, really big distances. So 4.2 light years is 4.2 times this number of meters. The other thing we're going to need in this problem is the Lorentz factor. Here I'm computing the Lorentz factor. Remember, the Lorentz factor is 1 divided by the square root of 1 minus v squared over c squared. All I've got to do is fill in v and c. I filled in v and c. It was easy here because I was actually told this number 0.95 is the ratio of v over c for the space rocket. And so I plugged 0.95 in here. Gamma here is 3.2. Time dilation here, length contraction here is not small. Your gamma factor is 3, over 3. So it means that times are going to, time dilation effects are going to be a factor of 3 dilation. Length contraction effects are going to be a factor of 3 contraction. There's big effects at these high speeds of 95% of the speed of light. I want to make a few remarks about solving the problem. There are 2 frames of reference in this problem. One frame of reference is the Earth Alpha Centauri frame of reference, right? Remember, I'm staying at home? That's a frame of reference, like the platform frame of reference. The other frame of reference is the astronaut's frame of reference. There are heading out, doing whatever they want. That's the second frame of reference, so it's like the train frame of reference. So there's two frames of reference here. They're both moving with respect to one another. One's not special and the other's not special. One's not privileged, the other one's not privileged. They're both perfectly valid reference frames, both moving at 95% of the speed of light with respect to one another, both described by a gamma factor, Lorentz factor, that's 3.2. So that's an important point. Times. There's proper times in this problem, and there's dilated times in this problem. This is a key to solving the problem. The astronaut measures the proper time. The spouse, that's me, I measure a dilated time for the trip. Why is that? In the astronaut frame, the location in their frame where they leave from, which is the center of the spaceship, and where they arrive at, Alpha Centauri, is actually the same location. In the astronaut frame, they didn't move, and their clock measures the proper time between, when they waved goodbye to me and when they called me up from Alpha Centauri when they got there. So the astronaut has measured the proper time because in the astronaut reference frame, departure and arrival are the same locations. And so the clock in their spaceship measures the proper time between those two events, the departure and the arrival. So that's really important. They measure the proper time. I'm going to record the dilated time. On the other hand, I measure the proper distance between the two locations. So it's in my reference frame as the spouse left at home. I measure the proper distance between the star and the Earth because in my reference frame, the star and the Earth are stationary, basically stationary. And so I measure, because imagine a meter stick, or a tape measure that went from the star to the Earth. That's stationary in my reference frame. That's going to measure the proper distance. The astronaut, my spouse, is going to measure the length contracted distance. So the astronaut is going to measure the length contracted distance. So look, these are the keys to solving the problem. To recognize, so this is a really important point, because I'm not doing any of the numbers yet, but you've got to, in relativity problems, you're always going to be dealing with two reference frames moving with respect to one another. You've got to know who sees the proper time, who sees the dilated time. You've got to know who sees the proper length, who sees the contracted length. That's the key. Once you get that straight, then the algebra is straightforward. But it's hard. It's really hard. It's hard for me. It'll be hard, I'm sure, when you look at problems. Who's the proper time? Who's the proper distance? Who's the contracted distance and dilated time? Gosh. Okay, this is just a point that no matter what frame, you agree on the laws of physics. The law of physics we'll use in solving this problem is simply that speed is distance over time. So the laws of physics that go into solving this is nothing in terms of speed being distance over time. It's just that we've got to understand these proper times, dilated times, proper length, contracted lengths. Okay, so here I'm just going to end up by showing you how the question asked, after all that discussion, nobody has any clue anymore what the question actually asked. I don't have any clue, you don't have any clue, we're all hungry. The question asked, in the spouse reference frame, how long did the trip take? So remember, I'm the spouse, I'm at home. How long did I see that trip take, measure that trip to take? In the astronaut reference frame, how long did that trip take? So we're going to figure that out. Now, I'm going to calculate the time that the trip took to leave Earth and arrive at the star just based on this law of physics. The laws of physics hold in all reference frames. I know the distance between the Earth and the star. That's that proper distance that I see the spaceship take. And I know that the speed that the spaceship is traveling at. And so all I've got to do to calculate the time in my reference frame is divide the distance traveled, which I'm told, by the speed. And I calculate 4.5 years. Look, this is a solution to that part of the problem that you would have done in the first week of Physics 211, calculated the time taken based on the distance traveled and the speed. It's just suddenly become really hard because I messed you up with time dilation and length contraction. But this first part of the problem, to figure out the time that I observed the trip taken, is just distance divided by speed, because in that frame of reference we know the distance and we know the speed. The second part of the problem is how long did the astronaut think that measure the trip to take? And this is the key relativity bit. Remember, we said that the key is the astronaut sees the proper time. The observer on Earth sees the time dilated time. And so I'm going to use this equation for time